In this set of notes, we're going to look at what is called the definite integral. So to start out, we're going to define what's called the area problem. Now your book looks at problems of finding area under a different application that I'm going to look at here. The application that I'm going to look at here deals with probabilities, and so biostatisticians work with this type of area problem quite often. So in probability, the probability density function, or the PDF, of a random variable can be used to determine the probability that a random variable takes a value between two specified values. And one of the most well-known PDFs is what is called the normal curve, and you've probably heard of a normal curve before. So normal curves have the following shape, and they're defined by the mean and the standard deviation. Now with a normal curve, the mean occurs right at the center. But normal curves, the standard deviation controls how spread out it is. So you can have some normal curves where most of their mass is right above the median, or you could have other normal curves that are really far spread out. And all of these, the three curves that I've drawn here, these three would all have the same center, but they would have different standard deviations. Because again, this middle one that I drew, all of the mass is really close to the mean, so that would be a small standard deviation, and then ones really far out are spread apart and they have larger standard deviations. Now here's what the formula for the curve looks like. And again, that area under the curve represents a probability. Now a probability, or the probability of an event, is always between 0 and 1. So a probability of 0 would mean that something never ever occurs. There's no possible chance of it occurring. Whereas a probability of 1 is something definitely occurs. It occurs all the time, no matter what. And then of course, we have values in between 0 and 1 to indicate, things that happen only part of the time. And so it ends up that a normal curve, again, it helps us find probabilities, and the area under the curve is what dictates those probabilities. And so the total area, if we were to fill in all of the area of a normal curve, so all of this would be a total of 1. And we're going to look at an application to hopefully help this make more sense. And we're just introducing this idea of the normal curve here as a motivating example, but you'll work a lot with this idea in BST 675. All right, so there are many biological functions that follow a normal distribution. And so, for example, the length of human pregnancy is not fixed. It's known that it varies according to a distribution, which is roughly normal with a mean of 266 days and a standard deviation of 16 days. So one way to think about this is if we were going to randomly select a pregnant woman and we were interested in how long her pregnancy was going to be, we know not all women have a pregnancy of exactly the same time length. It's going to vary some. And what this probability curve helps us do is it helps us to figure out, okay, when I go to randomly select that woman who's pregnant, what is the probability that her duration of pregnancy is between certain values? And so questions that a distribution like this can help us answer would be things like, what is the probability that a randomly selected woman has a pregnancy between 250 and 270 days? What is the probability a randomly selected woman has a pregnancy less than 230 days? And what is the probability a randomly selected woman has a pregnancy more than 310 days? So in terms of our distribution, how we would go about finding those values or those probabilities is we would actually look at the area that occurs underneath of the curve. And so for example, if we wanted the probability that a randomly selected woman has a pregnancy between 250 and 270 days, what we would need to do is find the area underneath the curve. In other words, we want this area here. And now again, for a normal curve, the total area is equal to 1, so I know that this area is something less than 1, but I need to find a way to find that area. And there, again, are other applications where you want to be able to find areas under curves. And that's really going to be our focus of this chapter, is given a function, how do we find the area under the curve when you can see that area is the area under the curve all the way down to the x-axis. And so the question is, how do we find those areas? And so again, if we think of that problem we just looked at, how do we find this area between 250 and 270? Now, one possibility to approximate that area, they wouldn't find the area exactly, is we could use rectangles to help us out, because we know how to find the area of a rectangle fairly easily. So one possibility that we could do is we could notice that the width here from 250 to 270 is a width of 20. And then maybe I just want to use this rectangle right here, if I were to shade this in, to estimate the area under the curve. And why I might use this rectangle is because notice, if I evaluate this function at 250, if I evaluate the function, I know exactly how high this rectangle is. And it looks like its height is just at 0.015. So I could find the area of this rectangle by taking 20 times 0.015. But we can see from this picture that using that single rectangle, I'm obviously missing a good piece of area, so that might not be the best way to approximate that area. But what if instead of one rectangle, I use two rectangles? So maybe instead of just considering one rectangle of length 20, or width 20, I considered two where they each had a width of 10. And then now my new rectangles are going to look like this. And so again, I can very easily find the area of these rectangles, and I can see that by having two rectangles, I have a better approximation. So keeping with that theme, what if instead of two rectangles of width 10, I looked at four rectangles where they each had a width of 5? And so my drawing is not great here, but we'll get the idea. I looked at these rectangles. And so we can see as I increase the number of rectangles, I'm going to get a better and better approximation of that area under the curve that I'm interested in. And so for the rest of this section, we're really going to focus on how do we find areas under the curve. And we're going to pause this discussion of probabilities. And then when you take BST 675, you'll pick up that conversation about probabilities, but you'll then have the tool set to really be able to find areas under the curve to help with that conversation. All right, so we're going to talk about what are called Riemann integrals. So the general theory of Riemann integrals takes a similar approach to finding the areas as rectangle method above. And so for example, suppose that we wanted to calculate the area, and that should say instead of between the curve, it should say under the curve. And here's what our curve is between -3 and 4. So looking at our picture here, let's mark where -3 is. So -3 occurs right here, and 4 occurs here. So notice between 0 and 4 that our function lays above the x-axis, and from 0 to -3, our function lies below the x-axis. So for areas that are above the x-axis, we say that this portion is going to contribute positive area. For areas below the x-axis, we say that we have negative area. And so to use this approach, if we're going to use our rectangle approach that we just saw, one important thing is that our rectangles have to be equal width. And so you'll notice in this last example when I was talking about, I started out with one rectangle of 20, or two rectangles with a width of 10, or 4 with a width of 5, but in all cases I kept the rectangles having equal widths. And so we are going to want to do that here as well, and we're going to try to estimate that area underneath of the curve. And so let's see what that is going to look like. All right, So what we're going to do is we're going to define rectangles using what are called Riemann sums for the function. And your book gives some more detail on this, so again, do make sure that you read through that example as well, but I'm going to give the general idea here. So the general idea when we're using a Riemann sum is we're going to set up rectangles that all have equal width. And so you'll notice in this sum we have W over and over again. That represents the width of each of the rectangles. And then the function evaluated at different points is going to represent the height of the rectangles. So let's see what that would look like for this function here that we had from the previous page. So again, we were interested in the area from -3 to 4. So if we're going to set up our rectangles where they each have width 1, let's draw what those rectangles would look like. So the first rectangle, we always start from the left and move to the right. We notice if we're going to move up one space, how this rectangle is going to look is we start on the left-hand side where the rectangle meets the function, and then we draw our rectangle. We do the same thing for the next one. We start from the left, we see where the rectangle meets the function, and then draw the rectangle. And we keep on doing this. Right, and then I'm just going to shade these in. Oops. There we go. And so these rectangles are going to help us approximate this area under the curve. And so notice for those negative area places, we're actually going to overestimate the area under the curve. And for those to the right, we're actually going to underestimate the area under the curve. Now, if we look at how we're going to calculate the area of these rectangles, notice that for the first rectangle, the height of this rectangle is given by the function evaluated at -3 times my width of 1. The area for the second rectangle is given by my function evaluated at -2 with a width of 1. The area of this third rectangle is the function evaluated at -1 times 1. So notice for each of these I'm taking the height times the width of the rectangle to get that area. So this is how the Riemann sums are calculated. So notice here that my function, and this was written on the previous page, is equal to 1/10 times x to the third. So if I'm going to set up that Riemann sum, I'm just adding up the area of each of these rectangles. So my first rectangle, the height was the function evaluated at -3, and the width was 1. So that gives me the area of the first rectangle. And then I can go on to get the area of the second rectangle. And I can keep on going. Now, one thing to be careful of, though, is where the last rectangle falls. Notice, looking at the last rectangle, we have 3 right here and 4 right here. So to find the area of this last rectangle, this is f of 3 times the width of 1. So the function evaluated at 4 never appears in this summation because the function evaluated at 4, which notice that occurs all the way up here, doesn't actually, isn't the height of any of the rectangles, so it isn't used. And so then here, if we were to go through and actually calculate each of these, so for example, to take 1/10 times -3 cubed, we would have -2.7. And if we kept on going, these are the values that you would get. It ends up, in this case, that the positive area for this function cancels out the negative area, and the area under this curve is actually 0. Now that isn't always the case, it just ended up here we were symmetric, and so those areas ended up canceling each other out in this approximation. But your book will show another example where that doesn't happen. But just know if you do get an area of 0, that isn't necessarily wrong. It is possible for your positive area approximation to cancel out your negative area approximation. And so the Riemann sums form a sequence, and if that sequence converges as n goes to infinity, we have what's called a definite integral. So what does it mean in words for n to go to infinity in this scenario? For in this scenario, when we talk about n going to infinity, that is the same thing as using an infinite number of rectangles. And if we go up to, again, that very first example that we looked at, remember that we talked about as we made the width of those rectangles smaller and smaller, in other words, we used more rectangles, we were going to get a better approximation of the area under that curve. Well, that's exactly what's happening here when we talk about taking the limit as n goes to infinity. We're talking about using an infinite number of rectangles, which is going to give us the best approximation possible. And so this leads us to the definition of what's called a definite integral. So let the points x0 equal a be less than x1, less than x2, and so on up to b, divide the interval from a to b. So this first sentence, all this is saying is that if we think of our function, our two endpoints are going to be a and b. And then what we're doing with that x1 through xn is that is going to be, you can think of those as all the places where we're going to put rectangles in between a and b. And so that's why it's dividing the interval a to b into n even subintervals of width. And then notice the width is going to be b minus a divided by n. So where does that come from? Well, if we think of a number line from a to b, if we're going to have n different dividers in here, well, the length of this interval is b minus a, and then if we divide by n, we're going to get the width of, the individual pieces, or in this case, the width of each of the rectangles. So then we define what is called the definite integral. So we have some new notation here. This kind of stretched out looking S notation, this notation right here, that is called the integral sign. And the integral is going to represent the area under a curve. And so we could say that the integral over the interval, and we start from the left-hand side of the interval up to the right-hand side of the interval. So we're going to integrate from a to b of the function, so we're going to put our function in here, and then we're integrating with respect to x. So similar to how we differentiated with respect to x. That's where that's coming from. Well, what that integral is going to be equal to is here, notice you have that Riemann sum, and so we're going to take that Riemann sum, but we're going to look at the limit as n goes to infinity. In other words, we're going to look at that Riemann sum, but we're going to have an infinite number of rectangles. And notice here at the end of that Riemann sum, you've got xn minus 1, you don't have xn, and that is the same reason as in this example where we didn't evaluate the function at f of 4, we evaluated f of 3, because our last rectangle is going to be one step back from that right-hand endpoint. And then notice that simplifies to this. They've just simplified it into summation form is all they've done there. All right. And so it ends up that all continuous functions are Riemann integrable. So in other words, we can find the integral of them. So in other words, if f of x is continuous on a to b, then that interval is going to exist. And so we'll spend some time in this chapter talking about ways to find integrals. And you're going to find out in the next section in 6.2, it's actually related to that idea of the antiderivative that we saw in section 5.10. All right, so here we're going to express the definite integral from 1 to 3 of the function e to the negative 2x dx as a limit of Riemann sum. So we're just going to practice that limit notation here. So the first thing to notice is we are interested in the interval from 1 to 3. right? So if we start out by writing our integral, so we're going to go from 1 to 3, and we're going to integrate the function e to the negative 2x dx. Well, by definition, that's going to be equal to the limit as n goes to infinity. And now what we're going to do is we're going to evaluate e to the negative 2x at all of the different points. But we have n different points that we're going to evaluate. So the first one is e to the negative 2x naught. Then we would evaluate e to the negative 2x1, e to the negative 2x2, all the way out to e to the negative 2x to the n minus 1. Because remember, we don't evaluate the function at n minus 1. And then this limit will be multiplied by w. Sorry, that's running off the page there. And w is going to be equal to 2 divided by n. So why would w be equal to 2 divided by n? Remember that the idea here is that we've got this interval from 1 to 3, and we're going to split that interval up into n different rectangles. So if we're looking at the interval from 1 to 3, notice from 1 to 3 has a width of 2. So that's where the 2 comes from. And then we're dividing it into n rectangles. And so if we do that, the width of each of those rectangles is going to be equal to 2 over n. And we know that the starting point of the interval is equal to 1, and the end point is equal to 3. And that all of those points that we're going to be interested in, and again, we're listing them kind of as arbitrary points right now, because we're going to break it into n, and we don't know, n is going to go to infinity. But all of those points are going to divide the interval from 1 to 3, oops, square bracket there, into n even subintervals of width w. And so if in your homework, if you're asked to take an integral and write it as that limit of Riemann sums, that's just direct application of this definition right here. All right, so let's talk more about the geometric interpretation of definite integrals. So remember that anytime we're working with an integral, what we're interested in is how much area is under the curve. And again, when you get into like BST 675, that idea is going to become very important, and it's going to be very useful. So here we have a couple different pictures, and these come from your book. So in the first one, here we have the area of a region under the curve of a positive function. And so for a positive function, we're going to evaluate from A to B, and we're going to look at the area between the curve and the x-axis. And that's going to give us this integral right here. Now, the area of a region above the curve of a negative function is actually given by negative A to B f of x dx. And again, that's because we're going to have negative area. And then we might have a mix between the two. So if f is integrable on the interval from a to b, and the function is strictly greater than or equal to 0, then the integral is going to be equal to the area of the region between the graph of f and the x-axis from a to b. On the other hand, if it's integrable from a to b, just in general, and you notice we're not placing any restrictions on whether or not f of x is positive or negative here, then it ends up that that integral is going to be equal to the area above the x-axis minus the area below the x-axis. And that's exactly what we saw earlier on pages 3 and 4 when we looked at that example with those rectangles. So we're going to look at two examples here where we're just going to use the graph to give an interpretation of what the definite integral looks like. And so here we're not actually calculating anything. This will be just looking at what that area under the curve would look like. And so this is going to be very similar to your textbook problems from number 30 to number 36. So in this example, we want to use the graph to interpret the definite integral, where we would be interested in integrating e to the negative x between 0 to 5, or in other words, on that interval from 0 to 5. So here we have 0, up here we have 5, and so the area under the curve would be this area right here. And so notice in this case, this whole region would be positive area. Looking at this one, here we would want to interpret the definite integral from -2 to 3 of 1/2 x to the third. So again, we're interested in -2 to 3. So here we have -2, and here we have 3. So the area under the curve would consist of this area and this area. And so notice for this integral that the area above the x-axis is again positive area. The area under the x-axis, this is negative area. And if we were to want to take the total area, we would take the positive area minus the negative area. So let's look at some properties of Riemann integrals. And so we have 8 different properties here. Your book does provide proofs for some of these, so again, as always, I recommend reading through that section. So the first property says that if you're going to integrate a function from a to a, so notice here in the integral we have a's both at the top and at the bottom. Essentially what this is saying is the area between a and a is 0. The next one, what we're doing here is notice we have an integral from b to a. So we have an integral from b to a, but we're going to switch that from a to b. If we're going to do that, we need to place a negative sign in front of it. And the reason for this is we're reversing the direction of the integration, and if we reverse the direction of the integration, it's going to become negative. Looking at the third property, notice in the third property we have if k is a constant, and here we have k times a function, we can pull that constant outside of the integration. The fourth property looks at if we have a sum of functions, so if we're going to integrate a sum of functions, that's equal to the sum of the integrals. The next one, what it says is, let's say we're interested in integrating over the region from a to b, but there is a number c in the middle. Well, the area over the function from a to b is going to be equal to the area from a to c plus the integral from c to b. So in other words, if we think of, if we were to draw a curve over top of this, and then we could think about what that area that we're interested in looks like. Essentially, all this fifth rule is doing is it's saying, well, we could always just break that area into 2 pieces and we could add it together. Looking at the sixth rule, this one is just saying that if a function is always greater than or equal to 0 on a to b, then its integral must be greater than or equal to 0 on a to b. And so again, if we think of a graph, remember that an integral tells us the area under the function down to the x-axis. So of course, if f of x is at or above the x-axis, then we know that the area underneath of f of x has to be at or above the x-axis. This one is saying that if f of x is always less than or equal to g on a to b, then the area under f of x must be less than or equal to the area under g of x. So similar idea. So let's say I've got a function f of x and I have a function g of x, to where f of x is always less than g of x, then of course the area under g of x is going to be greater than the area under f of x. And so that is what that seventh rule is saying. And then finally, my last rule here, it says if little m is less than or equal to f of x is less than or equal to big M on a to b, then m times a minus b must be less than or equal to the integral from a to b of f of x dx less than or equal to big M b minus a. So what exactly does this one mean? So this one, what we're saying is, let's draw a little graph here. And along the bottom, I'm going to have a to b. And then what I'm also going to do here on the y-axis is I'm going to define a little m and a big M. Okay. And so the first thing I want to do is let's just draw what little m times a minus b and big M times b minus a look like. So the first one we're going to draw is the rectangle that falls between a and b and goes up to little m. Well, notice that the area of this purple rectangle is equal to little m times b minus a, because b minus a gives me the width along the bottom and little m gives me the height. On the other hand, if I look at the rectangle defined going between a to b and big M, that rectangle is going to look like this. And notice that is equal, again, for similar reasons, big M times b minus a. So what is this rule really saying, or this property really saying? So in the first part, we know that f of x is always less than or equal to, or is really between little m and big M. So in other words, if I were to draw my curve is always going to fall between big M and little m. And then what this part is saying is it's saying, well, if my curve always falls between little m and big M, then my area underneath of the curve must fall between, in this picture, the orange rectangle and the purple rectangle, because the blue area would look like this. And so that's what property 8 is saying. So let's look at an example where we are going to apply some of these properties. All right, so we are given that the definite integral from 0 to a of x squared dx is equal to 1/3 a cubed. So the first one we want to find is the definite integral from 0 to 1 of 1/2 x squared dx. Well, notice that 1/2 is a constant, and so by property 3, we can pull that constant out. So we're going to have 1/2 times the integral from 0 to 1 x squared dx. But notice that I'm given that the integral from 0 to a x squared dx is equal to 1/3 a squared. Well, in the example that we have here, we have the exact same thing. It's just that a is equal to 1. So we know that this is equal to 1/2 times 1/3 times 1 cubed, which is equal to 1/6. Very similar for the next example. Here we want the integral from 0 to -1 of 3x squared dx. Well, 3 is a constant, so this is equal to 3 times the integral from 0 to -1 x squared dx. Well, again, we can apply our given information that we have right here, and in this case, a is going to be equal to -1. So this is going to be equal to 3 times 1/3 times -1 cubed, which is equal to -1. And again, we applied property 3 here to pull out that constant. The next one, we're interested in the integral from 1 to 1 of 3x squared dx. Well, notice that this is going to be equal to 0 by property 1. And that's because we're integrating from 1 to 1, or from a to a. In other words, if we were to think of our number line, or we could even say a graph here of our function, we don't have an interval running from a to b. We really just have this dotted line above a, which has no area above it, and so that's why that's equal to 0. The next one we've got here is the integral from -1 to 2 of 1/3 x squared. Well, we can start by applying our third property and pull out that constant. Now, in order to apply my given information, I need an integral that runs from 0 up to some number. But here I've got -1 to 2. So the next thing that we could do is actually apply that property 4. And remember that property 4, what it did was it said if you're interested in integrating from a to b, you can break that into 2 parts. So this is going to be equal to 1/3 times the integral from -1 to 0 x squared dx plus the integral from 0 to 2 x squared dx. Now notice the second one runs from 0 to 2, so that looks like our given information. But our first one goes from -1 to 0. So we really need 0 to be on the bottom. So notice we could then apply property 2. And so property 2, if you'll recall, that's the one that allows us to switch the a and the b, but we need to put a negative sign out front. So this is going to be equal to 1/3 minus the integral from 0 to -1 x squared dx plus 0 to 2 x squared dx. And so now these are both in the format of our given information, and so this is equal to 1/3 times 1/3 times -1 cubed plus 1/3 times 2 cubed, and you can find that's equal to 1. All right, one last example here. So here we're interested in the integral from -2 to 3 x plus 1 squared dx. Now this one, we can't quite use our properties. We need to be a little bit more crafty with this one. And to see what we can do, let's actually look at the graph of x squared plus 1 squared and the graph of x squared. So here in red, we have x squared. Here in blue, we have x plus 1 squared. So notice that the graph of x plus 1 squared is the graph of x squared shifted to the left by 1. So the area under the curve x plus 1 squared from -2 to 3, and so if we mark kind of here on our graph where that would be this area here, all the way up to, it's kind of off the page here, this area here, is the same as the area under x squared from -4 to 1. Sorry, I misspoke there. I should have said from -1 to 4. That's going to be the same as the area from x. That is going to end up being the same area. So in other words, let me write that down. We have that the graph of x plus 1 squared is the graph of x squared shifted left by 1. So therefore, the area under x plus 1 squared from -2 to 3 is the same as the area from x squared from -1 to 4. So using our integral notation, what we're saying is the integral from -2 to 3 of x plus 1 squared dx is equal to the integral from -1 to 4 x squared dx. And then from here, we can apply the properties just like we did in this problem right here. And you would find that this is equal to 65 divided by 3. So as always, if you have any questions over this material, please let me know.